sense of the unknown has always lured mankind, and the greatest of the unknowns of today is outer space. The terrors, the joys, and the sense of accomplishments are epitomized in the space program. End of quote, Captain James Kirk. Today's space show, titled Aerospace Propulsion Part 2, we delve into the very niche factors which are the forces behind achieving interstellar travel. While the dream of advancement of human exploration beyond our solar system can seem too overwhelming, as we stated, today's episode, we will take you through what exactly happens at the grassroots level in making this dream a reality. Today, we have amongst us some of the greatest persons in the field of spaceflight and deep space exploration, beginning with Dr. Harold White, a mechanical engineer, aerospace engineer, and applied physics, who is the advanced propulsion team lead for the NASA Engineering Directorate and is known for proposing new Alcubierre drive concepts and promoting advanced propulsion projects under the development at the NASA Johnson Space Center. We also have with us Mrs. Holly Elizabeth Ridings, who's an American mechanical engineer and the first woman to be Chief Flight Director at NASA. And please welcome Max Meikler. He's a 26-year calculation engineer who is currently a PhD researcher working on satellite and rocket propulsion and simulation and analysis of deep space propulsion systems at the Bundeswehr at the University in Munich. So with this pioneers from the industry, we will be exploring the perplexities of aerospace propulsion and deep space exploration. So this session highlights also the advances in the systems and addresses some of the current state-of-the-art chemical and electrical propulsion systems. So now I have the honor to introduce you to our first speaker, Max Meikler. He has already been introduced. I'll hand the mic straight to you. You will be giving us an overview about this deep space propulsion systems.
Yeah, hello, I'm Max, and today I'm going to talk a little bit about deep space propulsion, the history, current research, and the future of interplanetary space travel. I'll also focus on not on really exotic developments, which are hundreds of years away perhaps, but my presentation is mostly about the current developments which can make it happen, to see it in the next decades that we will be able to do this. So the term deep space itself is really closely connected to this deep space exploration. So there's no border where deep space begins. It's just a term to describe in general some certain conditions that you have and huge distances that you want to travel to. And but before that, we have to define space and itself. So the term space itself is generally accepted to be at the von Karman line, which is at 100 kilometers altitude. And except the Apollo missions about 60, 70 years ago, all human spacecrafts like the ISS or Mir, etc., they all remained in low Earth orbit. And deep space itself is generally considered with every spacecraft outside of the low Earth orbit. So the low Earth orbit goes around from 100 kilometers to up to 1,000 kilometers. And yeah, so the Apollo missions, though, they entered the deep space regime while flying to the moon. And you have certainly different conditions than in low Earth orbit. So one of these conditions is that you have an extremely low particle density within the deep space regime. So with only 1 million particles per cubic meter, which is really, really low. We're talking about 2.5 to the power 25 in an ambient air here down on Earth. And to get into deep space, actually, you have to permeate the Van Allen belts, which is shown in these slides. So there are basically 2, sometimes 3, depending on the sun activity, belts which you have to cross. and they're generated by the magnetic field of the Earth. So when the solar wind, which is basically a stream of really fast and charged particles, when they hit the magnetosphere, they are aligned in a certain position, and they remain in these Van Allen belts. So you have to permeate these Van Allen belts, which can damage your spacecraft and also damage a human being, because you have much more cosmic radiation in this regime. And this brings me to my next slide. So outside of low Earth orbit, because these Van Allen belts, they really protect the magnetosphere of the Earth. They protect us down on Earth from this strong solar wind. And when spacecraft enter the deep space regime, they experience the constant stream of these really fast charged particles. So we're talking about protons and electrons, which hit your spacecraft with a velocity up to 1,000 kilometers per second. And that's really fast. And having this constantly, you need to address this with structural things and other things that protect the humans, perhaps, or the spacecraft itself. And as you can see in this picture, the Earth itself is mostly protected by the magnetic field that it generates within Earth's core. And that's why we can go outside without having these issues that spacecraft would experience in deep space. So the thing about why we really need new technologies when it comes to deep space is that chemical rocket engines themselves, they are really powerful, but the problem is they're not really efficient compared to other techniques when it comes to deep space propulsion. And so it's measured in the rocket regime. It's measured in specific impulse, and we're talking about 10 times more specific impulse, for example, for ion thrusters or electrical engines than compared to normal chemical rocket engines. And also, like deep space missions, they require a much greater velocity to escape the Earth's gravity. And it's also dangerous. So one of the downsides of chemical propulsion is that it's really dangerous to carry these fuels always with you, and they have to be liquid, so really cold. And also chemical rocket engines are really heavy and not redundant. So for example, if you have a electrical engines or a cluster of electrical engines, if one engine fails, then you still have a redundancy. And in particular for future human space flight, we're talking about the Artemis missions and perhaps Mars missions in the future. The deep space probes and also the space stations like Deep Space Gateway, they will rely heavily on other propulsion methods, such as electrical propulsion, like Hall thrusters or ion thrusters. But I'm going to talk about that. So when it comes more to exotic propulsion for deep space, there are several concepts also since the 50s coming from the US and then also from the Soviet Union in this time. So one of them was the Project Orion spacecraft, where you see an artist's conception here. And so what their thrust is basically to launch or to nuke and start nuclear weapons or atomic bombs behind the spacecraft. And this propulsion plate would protect the spacecraft from the blast, but also would the impinging amount of energy would push the generated thrust and push the spacecraft. But this is a really exotic concept, but it would work. There are several studies also carried out by NASA, and they might perhaps be in the future implemented. And yeah, so they're really also looking into nuclear engines. And what I'm working on, and what is right now mostly the de facto standard for satellites, also for orbit raising, and also the new Chinese space station is going to be entirely propelled in space by these ion engines. They are a group of engines belonging to the electrical engines. So the difference is to chemical rocket engines that they're 5 to 20 times more efficient than chemical rocket engines, because their velocity of the plume and exhaust is 5 to 10 times higher. So much more efficient. And they're easy to handle because they don't require any dangerous fuels. Mostly they use xenon or krypton to propel the engine. And they also require few amounts of fuel because they're so efficient. The only problem is that compared to chemical rocket engines, they're much less powerful. So we're talking about a maximum thrust from a 50 centimeter diameter iron thruster up to 5 newtons compared to millions or perhaps 1/1000 of newtons for chemical rocket engine. But these type of engines are really suited for Mars missions, and they're going to be implemented in most probes that are flying right now to outer space, such as Jupiter or Mars. For example, here you see one of the first demonstrators, which was the Dawn mission, which flew to the asteroid Ecoros in the asteroid belt, and it was entirely propelled by this iron engine, and it was proven that it works and that we can achieve great results when it comes to mission planning and efficiency, etc. And what I'm currently working on, so there's also propellantless propulsion systems, are solar sails and magnetic sails. So you have this regime where the sun ejects these really fast charged particles and also light. So solar sails, they utilize the thrust which is produced by light colliding with the solar sail, and they would either require a really high energy laser beam to be impinging the sail, maybe from a artificially created machine on Earth or in orbit, or they depend entirely on the sun's solar on the light ejected by the sun. The drawback is that they depend entirely on the distance to the energy source. So there's this famous formula 1 to the 1 over r squared. So with doubling your distance from the source, you have only 25% of the original thrust. But they're perfectly suited for long range and interstellar missions because the sail can be really, really huge. So you can a lot of light impinges then, so you have quite a high thrust when you have a really large sail. And compared to that, you have magnetic sails, so they are also propellantless, so you don't need any propellant to propel the spacecraft. And they generate their thrust by having a really strong permanent magnet or a oscillating magnet generated by an electric field inside the spacecraft, which creates an artificial magnetosphere around the spacecraft, such as Earth has it. But it's oriented in a certain position so that the positively charged protons, which are 1,000 times more heavy than electrons, that they impinge the magnetosphere and a momentum exchange happens. So you have a thrust generated only by the by the stream of the solar wind. And they're much more powerful actually than solar sails. And the good thing is, when we talk about deep space and interstellar travel, that also within space itself, out of the regime of the sun, you have a constant stream of charged particles with a really high energy, so you can utilize this to decelerate or accelerate your spacecraft. And why this hasn't been implemented yet is because you have to overcome structural and heat transfer issues for both magnetic sails and solar sails. But they are still developed, and I will later show you about which time frame we're talking about. So this is an artist's rendering of a solar sail, which I was talking about. So you have the sun on the left side here, and the light impinges the solar sail. And so the structural issues are mostly the sail itself, but also and it has to be really light and thin, but still be able to not break when the thrust is generated. And then you have propellantless magnetic sails. So this is a simulation from about 20 years ago by the most famous researcher when it comes to magnetic sails, which is Mr. Robert Wingley. And he was also working at NASA and doing lots of simulations and researching magnetic sails. So here you see the artificially created magnetosphere by the spacecraft itself, really similar to what Earth has. And the solar wind comes from the left side and impinges the spacecraft's magnetosphere here. And the magnetosphere itself from the spacecraft is about 10 to 100 kilometers in diameter. You're easily increasing the surface area in which the solar wind is able to impinge the magnetosphere. And to give you a short overview of the time frames that we're talking about, So when it comes to history and development, in the 1960s, the ion thrusters were developed here in Germany and also in Russia and America. And 10 years later, the Hall thrusters were researched and industrially applied later. And since the 1990s, the solar sails became a thing, and also the magnetic sails 10 years later in the 2000s. And they are all based somehow on, which is really interesting, on science fiction novels. For example, from Andrew Zubrin, who proposed this actually in a science fiction book in 1985. And then it was adopted by researchers 10 years later at NASA. And when you look at the current applications, you have the ion thrusters. So ion thrusters and Hall thrusters are currently mostly used for most of the probes that are flying to outer space and also for orbit raising and positioning. And so since the 2000s, they have been successfully proven to work. And then you also have Hall thrusters, which are kind of similar, but they have some minor differences when it comes to the generation of the thrust itself. And they're also used for example, for the Lunar Gateway, as NASA stated. And also solar sails have been tested since 2010, and so since 10 years. And they're really suited for long-range missions when you have CubeSats, for example, like the project Ecoros, which was launched in 2010. And when it comes to the future, we have the Lunar Gateway from NASA, and it's also propelled by electrical engines, combined with the powerful chemical engines. And in 10 years, there are several startups also here in Europe which are currently working on implementing solar sails for CubeSats. And also NASA was readopting the possibility of using nuclear engines, which are combined with chemical rocket engines. And this may happen in 15 years. And then you also have in 20 years, perhaps, the magnetic sail concept. So the main issue of magnetic sails is that the magnet itself is generating lots of heat. So you need a superconductor at a really high temperature, which is currently also researched. But there are lots of progress is made from this point of view. But it's actively researched also here in Germany, where I'm working, and we might see it launched in 20 years. So that's the time frame we're talking about. And so if you talk about interstellar travel, then perhaps magnetic sails, because they can decelerate and accelerate without any propellant, and you always have a stream of charged particles in deep space, might be the standard for interstellar missions, which can also be combined for example, implemented into CubeSats or also bigger missions, depending on what you would like to achieve. And to finish this presentation, I want to give you show you a picture of a real solar sail developed. So this is actual footage of the project Ecoros, which was launched by JAXA, so the Japanese space agency, about 10 years ago. And so this is a camera that flew out away from the spacecraft to photograph if it was actually working, the deployment of the solar sail. So since 10 years, we can say that we actively have these types of and project demonstrators that demonstrated that this development works, and lots of simulation work is also done. So it looks really promising. And the next 10 to 15 years are going to be amazing in seeing all this development. And I'm certainly, and I'm sure that within 10 to 15 years, these will be one of the propulsion techniques that will also be used for interplanetary and interstellar space travel in the future for deep space. So yeah, that concludes my presentation, and I'm very keen on and honored to work in for these types of propulsion systems.
Thank you, Max, for your deep space propulsion insights. Mm-hmm. And what are some of the current advancements in ion thrusters and magnetic sails?
Okay, so the main difference is that magnetic sails are under development, and it's more like an academical propulsion technique. And the ion thrusters have been demonstrated to work and to have gained a huge improvement compared to chemical rocket engines. So I'm also researching and working for some ESA projects regarding ion thrusters. So the main advancements which are currently implemented and utilized are the generation of the plasma itself inside the chamber. So you inject a neutral gas, then you have a plasmification. So you eject the electrons from the outer layer of the atoms, for example, xenon. So you have, and you only have about 2 to 3% of plasma inside the chamber. So the main issue of ion thrusters is that they're really efficient, but the problem is that the amount of plasma inside the chamber is really low. So we're only talking about 2 to 3%. So the current advancement when it comes to ion thrusters is mostly the generation of plasma and the plasma extraction, so the ion extraction through the grid, which accelerates the ions to produce more thrust, basically. And when it comes to magnetic sails, the most important advancements right now are the simulations. So you have a micro scale, so you have the protons with 1,000 kilometers per second hitting the magnetosphere of the spacecraft. And at the micro scale, so really small scales, but then you also have the big scales, so 100 kilometers of diameter, the magnetosphere itself. So you have to simulate holistically the whole multi-physics process, basically. So until now, it has not been able to numerically and computationally, the resources were not enough. So right now is the time when the resources are enough to simulate actually and estimate the thrust generated by magnetic sails, because they're actually really hard to simulate on Earth within an experiment, because they have to work within a really rarefied gas. So we're only talking about 1 million particles per cubic meter, and the best we can achieve on Earth is 1 to the power 15 particles when it comes to vacuum chambers, 1 to the power 15 particles per cubic meter. So mostly when it comes to magnetic sails, the advancements are about computational simulating and estimating the thrust generated by magnetic sails.
Thank you, Max. There's already many questions coming in from the audience, but hold back. Okay. We'll be able to answer them the second half of the show. Our next speaker, we're very honored and privileged to have Mrs. Holly Elizabeth Ridings dialing in very early today from Houston, Texas. That's where she resides with her family. She is America's first chief flight director at NASA. And you can now lean back and listen to her story, how she ended up where she's now. She has many, many special honors and awards, and extensive experience with the lead flight directing for Expedition 16 STS-127 and the first SpaceX Dragon mission to ISS. That was her. Also at the Expedition 16, Holly was responsible for the ISS crew during STS-120, STS-122, 123, and the first ATV mission. She also led 5 non-shuttle EVS primarily for PMA ISS construction and recovery from a solar array failure. So Holly, I'll hand it over to you. There's a long bio here, but I'm sure she can share it herself. She also served as the flight director office assistant for ISS and visiting vehicles before selection as the deputy chief of the flight director office in the fall of 2014. And prior to being selected as flight director, Holly was the lead for the ISS ADCO, which stands for Attitude, Determination, and Control Group. So it's an honor and privilege to have you dialing in today. Holly, I hand it over to you.
All right, well, let's see. Good morning, good afternoon, everyone. That was a wonderful introduction. You now know the first thing, important thing about NASA, which is we really like our acronyms. And so the bio and the introduction, is mostly just a bunch of missions that I've been privileged to work here. And certainly it's also a privilege to be talking to all of you today. So as was said, I'm the NASA Chief Flight Director. And so I've got a few slides, mostly pictures. They're going to talk about what does that mean, and then we're going to talk a bit about what's going on at NASA. So first and foremost, being the NASA Chief Flight Director means you're responsible for our human spaceflight operations. And the most important part of that is the men and women that work and live in space, our crews on board. So if I can start sharing here, I'll show you what that looks like. So right here, there we go. All right here is our crew that's currently living on board the International Space Station. You can see this picture was actually taken on Sunday. We just completed yesterday a series of 3 spacewalks in order to deploy some next generation solar arrays. And it's interesting, they look a bit like solar cells, or don't quite do the same thing that Max was talking about, but they do generate power for us, right? The space station was built, starting in the late 90s over multiple years. And so our solar arrays have degraded a bit. So now we've added some new ones, and that was a lot of work to get them out and attached and set up. So we did 2 over the last 3 spacewalks. So in this picture, you can see kind of over on the left is Shane Kimbrough, over on the right, that's Thomas Pesquet, one of our international astronauts. Aki Hoshide is in the middle. He's currently our commander. These are our Russian cosmonauts, and then that is Megan Binkin. So that's our crew that's on board right now. So being the chief flight director is really about making sure the crew members are safe in space. The next thing it's really about is the vehicles that they fly in and keeping them safe. And the third part is really, of course, all of the missions, the objectives that we're trying to complete in order to move forward and make progress with human space flight. So really, what does my job look like? Let's see if I can get this to advance. There's a pretty picture of the spacewalk, just because it's really, really fun. This is our truss over here, and obviously the guys out in spacesuits. The fun thing about this picture to me is these little tiny lines, those are their tethers. And so anywhere you work outside during a spacewalk, you have to be tethered. Obviously, you don't want to fly away from the space station. And so we string those all over our work area, and they go all the way back to the airlock. They're pretty far out at the edge of the space station here doing some work. So this is what it looks like for me. You can see, actually, I'm hiding right in the middle of this picture. On the left-hand side is our historic mission control. So one of the great things about NASA, lots and lots of history. It goes back to the 1960s, and this room right here on the left is actually where we did the moon landing. And so we're going to talk a little bit about the next moon landing that we're gearing up for, but this is our kind of historic room. And this is what it looks like today. So again, that's me. And then this right here is the Dragon vehicle coming to the space station, and it's going to dock right there to that port in the middle. And so yesterday, those screens were full of pictures of Thomas and Shane out in spacesuits. Today is actually a little bit of a rest day for the crew, since we just completed our three EVA series over the last 9 days. All right, so a little bit about how I ended up here. So I started out working at NASA as what we call a flight controller. So we think of it kind of as a 3-part system. You have the team that's in space, right? So that's your astronauts and your cosmonauts. You have the team on the ground in mission control, and then you have your spaceship, your spacecraft that they live and work in. And so the team on mission control is led by a flight director. And so, of course, that's me on the right. On the left in the inset is actually Dr. Chris Kraft, who was the very first flight director. And so if you go to Mission Control in Houston, which I hope you get to visit someday, you can see his name up on the building. And so he's really kind of the founder of all of the things that we do today. He started out as a test engineer. And so operations and flight operations is a very technical area, but it's also where many of the other skills, come into play in terms of communication, quick decision making, risk management. And so we have a team of 25 to 30 flight directors. Right now there's 27 who sit here in mission control and run the team on the ground, make sure the crew is safe, make sure we get our missions done. And so several years ago, I was asked to become the chief flight director. There's been 13 chiefs over the course of history of human spaceflight. And so obviously it was a very big honor to be selected to do that and be the first female to do that job. It's a pretty amazing job, because if you look at this slide, these are all of the spacecraft that we take care of today, and the list is growing. In fact, I probably missed one if I look at this slide really closely. Most of these on this picture are low Earth orbit. If you have the space station here kind of in the left center of the page, you know, on the far left side, Russian vehicles that come to the space station, the Soyuz and the Progress. On the top, we've got a cargo vehicle built by a commercial company. On the bottom, you have a cargo vehicle, the HTV, built by the Japanese Space Agency. We also are in the process of adding crew-rated vehicles to the portfolio. So the SpaceX Crew Dragon, the very first launch of that was a year ago, May of 2020, in the middle of the pandemic, which was, of course, very challenging, but very successful, with Bob Behnken and Doug Hurley flying to the space station for several months. And since then, we've launched 2 more of those vehicles to the space station, and some of the crew that you saw earlier in the picture actually arrived on a Crew Dragon and will come home in the fall, in October. The Boeing team is also building a crew vehicle that will fly to the space station, and we're gearing up for an uncrewed test of that vehicle here, hopefully this summer. And so it's really busy time in low Earth orbit as we really transition some of what NASA's done historically over to commercial companies, continue with our international partners, and sort of push the boundaries of what people do living and working in low Earth orbit. On the right-hand side of this picture, you can see our exploration programs, and we're going to talk more about that in the next couple of slides. So along with our low Earth orbit portfolio, NASA in recent years has been working very hard in order to put together we'll call it deep space, because that's the word that Max used, deep space portfolio outside of low Earth orbit, headed to the moon here, hopefully in the not too distant future, and then on to Mars. And so we'll kind of walk through what that looks like. The first piece of it over on the left-hand side is the Space Launch System. And so this is a rocket that will get you, again, out of low Earth orbit and head up to the orbit around the moon. The rocket itself, of course, doesn't go that far because it goes through different staging, you know, first stage, second stage. But we do have that system assembled that will get the vehicle on the right-hand side, which is the Orion vehicle, out to deep space to be able to orbit around the moon, which we're pretty excited about. And so although getting humans to the moon is still several years away, the first launch of this Orion vehicle, hopefully later this year, we're really into the tactical time frame, gearing up to get that mission done. And so what that means to me, when I lead operations, you know, we're doing simulations. You start into what we call readiness reviews, where you really look at all of the technical aspects of the mission and the risk associated with it. Of course, flying in space is always risky, so you're always accepting some amount of risk, but certainly you want to make sure you understand that and try to minimize it as much as possible. And so later this year, this rocket will have this spacecraft on top of it. It's not crewed yet. So typically in a test campaign, you'll do a mission with a vehicle without humans on it, so an uncrewed test flight. And that way you prove out that the system is as safe as it can be before you commit human lives to the launch and to living and working on that vehicle. So after we get Orion up and working, we're putting together the next step, which is called the Gateway. So this is you can think of it as a small space station with some important differences. One, it doesn't have people on it permanently like our low Earth orbit space station. Our low Earth orbit space station has been continuously manned now for 20 years. And so this one is a little bit different. It's more like a way station. You know, imagine you're taking a really long hike and you need somewhere to stop for shelter, you know, maybe food or fuel, and then, you know, you keep going. And so it's a little bit more of a waypoint. So this is an artist's picture of Orion coming up to the Gateway. Now the Gateway, a lot of work has already been done. NASA has contracts with various companies, And so much of this is in production to be launched here in the next couple of years. And so that's really exciting because the entire goal is to make this sustainable. When we went to the moon, you know, back when at least I wasn't quite born yet, and many of you were probably not quite born yet either, or certainly much younger. We didn't put sustainable infrastructure in to stay, and so eventually that program ended, and then we stopped going to the moon. So the idea is to try to build the infrastructure, and some of what Max and what Sonny after me will talk about are the real important, you know, technology components that are going to come online here, hopefully, you know, in the next 5 to 10 years that make this all sustainable. So for us, the gateway is an important sort of first step in that direction. The other thing we need, wrong direction. The other thing we really need is a lander. So there's been a lot of discussion about landers. This is obviously an artist's rendition of the lander. NASA, in fact, did put out a competition for a lander, and it was won by a company, SpaceX, and currently being protested, and so that's all public knowledge. So we can't talk much about the details of the lander other than it is a critical component of the Artemis campaign to the moon. You obviously want to get to orbit around the moon. You have your gateway, your waypoint where you can stop. Some crew could stay up there if they need to, but you have to get down to the surface. And so for that, we need a lander. A lot of work is going on. You know, my job is really interesting because so much of it is very, you know, tactical, day to day. You know, what is the crew on orbit doing? You know, yesterday was a spacewalk. You know, tomorrow will be something different. And you're working in mission control, and you have all these vehicles coming and going to the space station, some of them for cargo, some of them bringing people, and it's really a hub. I mean, we do probably 12 vehicles a year, 24, you know, launches and landings, or, you know, rendezvous and undockings, if you think about it that way. And so it's very, very busy. So that's a big part of my job. The next part of my job, I'm gonna turn my video back on. There we go, since we're done with the slides. That, you know, the other part of my job is really almost at the other end of the spectrum, where, you know, we're working on all of the vehicles that are need to come online for the sustainable infrastructure for the moon and Mars. And so, you know, the last piece of that really is everything you're going to do on the surface, right? So we take our Space Launch System, we launch Orion, it flies to the moon, we have the lander and the gateway, we get down to the surface, but then, you know, what do you want to do and how do you do it? And so there's an entire, you know, teams of people and sets of research going on, you know, for things like spacesuits. As an example, you might need unmanned rovers to help you do work on the surface. How do you build up enough infrastructure where that becomes a destination that you can continue to grow over many years into the future without having, you know, to carry everything with you, like you're backpacking again, you know, into the woods, you carry everything in, you carry everything out. Well, that's an inefficient way, you know, to live if you want to, you know, build a house and kind of stay in that location. And so folks are really working on what we want that to look like, you know, which even as the chief flight director, we get involved in, you know, having this vision of how we'll operate it in the future, what the crews need to, you know, have available to them in order to be able to stay safe, to live and work successfully. And so, you know, it's a really, really exciting time to be at NASA, because you know, if you think of, again, projects, and they start out as ideas and then someday, you know, they turn into, you know, something you see on your shelf, or in our case, a mission. Right now you can work anywhere along that timeline, and it's really, really exciting for all of us. So that's kind of the super quick overview of at least, you know, how I ended up here, my job, and what's going on at NASA. And so maybe I'll hand it back and see if there are any questions.
There are many questions. Thank you, Holly. You're like a hero for many young women and girls. I just wondered, what did you dream of when you were a child?
Yeah, so actually, I wanted to work in human spaceflight since I was really young. You know, a lot of people who work in space, you know, have what, you know, we call an origin story. Like, you know, why did I get interested in space? And so, you know, for me, I was in the 6th grade so now, anybody who can do math live, you can figure out, you know, how old I am. But I was in the 6th grade when Challenger happened. And I remember sitting, you know, in the cafeteria in the elementary school watching it live. And of course, if you're not familiar with Challenger, you know, that was the first shuttle that we lost on NASA and on launch, and no one survived. And so, you know, that made a huge impression on me. I'm one of those people who, you know, wants to solve problems. Some people saw that and said, I don't want anything to do with space. You know, I saw that and said, hey, I want to figure out how to make that better. Now, you know, maybe in my 6th grade brain, it wasn't quite that clear, but in general, you know, that really stuck in my head in terms of wanting to, you know, be in the industry to, you know, solve really hard problems like that. I'm a team person. Like I also grew up playing team sports. And so, you know, kind of how I ended up in operations is the crossover between, you know, really technical work and then the people aspect of it. And if you think about it, those are really the two halves of operations, because you have to understand and take care of the systems, manage them, you know, command to them, figure out what to do with them, make a lot of decisions. The other thing is that, you know, operations can be pretty high speed in terms of your decision making. You know, you have to really like that kind of very fast paced environment. And so that ended up being the right choice for me. So I've been interested in human spaceflight since I was really young, and it was always my goal to work for NASA.
Thank you. If you review past your career, what's your secret sauce, or what is the shortcut to your career? I know many maybe are not as fortunate growing up with education. But what is the secret sauce and advice you would give for someone maybe who's not as lucky, you know, happen to, you know, there's many people that would love to work for SpaceX and NASA, but they're unfortunate with the citizenship, or, you know, so what is your secret sauce for anyone to, you know, just go ahead and implement their dreams? You know, what did never hold you back, and who were your role models when you most needed them?
Yeah, so the part where, you know, people are not as, you know, fortunate and maybe don't have proximity to space, right? So the really great news about space in general and human spaceflight is that it's growing in terms of participation, right? So it used to be just, you know, big governments. Now there's a lot of commercial, a lot of development of all kinds, big and small, in countries all over the world. So, you know, there are many places in the world that you can now get involved in some form of space, you know, work or research, even if it's not human yet, but still space research, you know, than you could, you know, 2 years ago, 5 years ago, 10 years ago. So, you know, in terms of people who are interested and don't feel like they have access, you know, the first thing I'd say is do research. I mean, Max was telling me, you know, before we started this about a company, you know, he knows doing space work in Germany. I'd never heard of it. I wrote it down. I'm going to go look it up. I mean, there really is a lot out there. So do the research. You know, in terms of me personally, I think the first thing is just work really hard, right? I mean, that sounds pretty basic, but I mean, I am tremendously stubborn. When I was young, I would not have claimed to be super great at, you know, math as an example. And so I just, you know, am really stubborn and you know, just worked really hard. That to me, looking back, you know, how I gained that work ethic, I probably credit my parents, which, you know, they've been amazing mentors and role models, you know, for me my entire life. Again, a lot of people don't have that opportunity with parents. And so the thing I tell all, you know, all students for sure is ask for help, right? So the thing, people love to help students, right? And young people, they you know, when you get older like I am, you start to, you know, want to share your network and share your resources with people. That's part of the value of sort of making it this far. You want to be able to make those connections. And so, you know, but you need to know that people are interested. So, you know, ask for help. Put yourself out there. You know, don't be afraid to, you know, go up and talk to people. And yeah, you know, sometimes it's not going to work, but sometimes it is. I mean, you have to be respectful, but certainly, you know, asking for help, trying to meet people, you know, putting yourself. I mean, I'm an introvert, and a lot of engineers are, and so I probably didn't learn that at a super young age. I mean, it was, you know, mid college and later when I finally really started feeling comfortable, you know, trying to actively learn from the people around me, you know, instead of passively learn. So go and ask for help. I mean, have a good attitude, and people will go out of their way to help you.
Thank you, Holly. Thank you. We have many more questions for you. But now our next speaker is Dr. Sonny. I don't think he needs an introduction. He's the, let me just pull up his bio here.
You don't have to read it. I can kind of do a quick bio intro if you'd like.
Yeah, you just go ahead and.
Okay. Yeah, let me get my screen up here. While I'm getting the screen up, so just you know, my name's Sonny White. I worked at Johnson Space Center from 2000 to 2019, supporting human spaceflight. Very exciting endeavor. I left JSC in 2019 to come join Brian B.K. Kelly here at the Limitless Space Institute as the Director of Advanced Research and Development. And so I'll talk to you guys a little bit about this today. But before I do that, I want to come back to a couple of comments that Max made and that Holly made, right? Just to talk about the importance of a kind of a crawl, walk, run mentality, if you will. You know, Max mentioned that the lunar gateway that's coming up, and Holly also talked about it. It has Hall thrusters integrated into the architecture to provide some propulsion for the system. And so back in 2013, I was part of a team kind of trying to define some of the next chapters of human spaceflight, and it went through several different names, one of which was Waypoint, oddly enough, but it ended up on Gateway. And so, myself and a number of other folks were working hard to educate, NASA leadership on the value proposition for integrating something like a Hall thruster into human spaceflight. I actually got the nickname Dr. No from that process because I would routinely ask to get some power for Hall thrusters, and they would tell me no. So, but as Holly said, sometimes it pays to be stubborn, right? And you just continue to try and advocate and let the facts speak for themselves. And so, based on those efforts, right now we have one of the next Lego bricks of the human spaceflight will have, a form of next generation propulsion, if you will, in the form of this Hall thruster concept. So, very exciting. So let me switch gears and talk to you about Limitless Space Institute now. So I joined back in 2019 to try and help stand this organization up and define it. Our mission at Limitless Space Institute is to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technologies. Our pinnacle objective, our North Star, if you will, is to try and work towards enabling interstellar travel by the turn of the century. And that is no easy goal. That is extremely difficult. When you think about space exploration, right, whether it's human or robotic, as you heard from both Max and Holly, right, it's difficult, it's challenging, and Max talked about chemical propulsion, right? If you want to send humans to the surface of the moon, and we're planning on doing that with Artemis, chemical propulsion can achieve that type of a goal. And we've got this beautiful example recently of sending a rover to the surface of Mars. We've got this rover that's running around on the surface of Mars, and that was all done through chemical propulsion. But if we wanted to send human beings to Saturn in 200 days, that's a very different challenge than the space exploration concepts I just talked about. The delta V to accomplish something like that is an order of magnitude higher than the delta V it takes to get a payload from the surface of the Earth into low Earth orbit. So chemical propulsion it can't close that type of a mission. And so if you want to talk about human exploration of the outer solar system, and maybe one day on to the stars. We have to have some significant advances in power and propulsion. So how do we do that? This is our capability chart. This is not meant to be comprehensive, but it provides some of the major brushstrokes to try and articulate how we might accomplish this type of objective, starting from what we know on the left to what we don't know on the right. So if I move my mouse on the screen, can you see that? It's on the top left here. In the left-hand swim lane, we have this title fission. And so that is a scenario where we have a spacecraft that has a nuclear heart. We've got a nuclear reactor. Nuclear electric propulsion is the acronym. And the nuclear reactor is providing power from the reactor to some Hall thrusters or ion engines. I think you heard Max talk about several different ways of doing electric propulsion. And so this type of a system using a nuclear reactor coupled to electric propulsion in the power regime of megawatts, 2 to 50 megawatts. This would enable us to send human beings to every destination in the solar system. The math and physics is very clear on that. And that's actually discussed in the literature by a number of folks that have explored how would we use something like nuclear electric propulsion to explore our solar system. We could even potentially enable what we call interstellar precursors. You see a number down there, 1,000 astronomical units. So an astronomical unit, that's the distance from the Earth to the sun. And so if you think that as a measuring stick and you line it up 1,000 times, that's an interstellar precursor type of destination that's been discussed in the literature. So nuclear electric propulsion, known physics, known engineering, we could potentially send humans everywhere in the solar system and even do interstellar precursors, but we really can't do interstellar with NEP, practical interstellar with NEP. For that, we might need to move a little bit into the unknown, right? So with with the same type of vehicle in mind, if we change the heart from a nuclear heart, if you will, to the same type of mechanism that's behind how the sun works, right? A fusion reactor. So we have potentially a fusion electric propulsion. So we just change out that reactor, the nuclear reactor, with a fusion reactor, and it's providing power to some electric thrusters. That type of a system will have much higher power levels than what we can potentially achieve with nuclear electric propulsion. And it will also enable faster human exploration of the outer solar system. And so if anyone's familiar with the TV show Expanse, that's the cartoon concept they used in that show is a fusion type of propulsion approach. And so the beauty of fusion is that this will actually also enable what I would call slow interstellar. It's still going to take, an appreciable fraction of a century if you had a fusion-based propulsion system for a spacecraft to take some human beings or a very large payload to another star system. But this is all based on known physics. We understand the physics. We just don't quite have all the engineering figured out. Now, if we wanted to try and really push the boundaries, right, to try and get somewhere to another star system in less than a human lifetime, we really need to be working on the frontiers of physics. So we're fully in the unknown. The engineering is definitely not known, and the physics is not understood. We haven't pieced it together. If you think of physics today, you've got basically kind of two standard models of physics: quantum mechanics on one side and general relativity on the other side. And so, these two models, they touch our lives every day in the form of, quantum mechanics gives us cell phones, general relativity gives us global positioning satellites. And so you can use a cell phone to go see a friend at a restaurant or something like that. So just this knowledge of physics, affects our lives every single day. But we know, since these two models are not fully compatible, there has to be a more generalized understanding to be developed. And so in the process of trying to explore and articulate that math and physics, could that maybe provide us some new insights where we could, maybe there's some way to interact with the manifolded space itself? Can we interact with and push off of space-time or the quantum vacuum? We know from general relativity that the idea of wormholes and space warps are mathematically possible, but we don't know how to build those yet. There's no way for us to kind of piece those together. So in the process of exploring the frontiers of physics, maybe we could find ways to make something like that potentially plausible or even practical at some point in time. So we here at Limitless Space Institute, we are a doing organization. And so, our pinnacle objective is to enable interstellar flight by the end of the century. And so the only way you do that is by, rolling up the sleeves and getting to work. And so we have several programs that are geared towards trying to achieve this type of work. We do work internally. We do R&D internally in our EagleWorks lab. We're currently funded by DARPA Defense Science Office doing some work on I guess in that rightmost swim lane, kind of the frontiers of physics. We're working on something we call our dynamic vacuum model. We also fund work externally through a program we stood up in the middle of last year called Interstellar Initiative Grants. This is where we fund external entities to do research in this domain across a broad array of topics. In this case, for our inaugural class of performers, we funded 9 teams. One is working on beamed energy propulsion. One is working on relativistic solar sails. We have 4 teams working on fusion propulsion, 2 space drive teams, and a team working on traversable wormholes. We also sponsor research at universities through our university partnership program. We're currently funding Texas A&M to do some work on a micro nuclear reactor that's in the 1 to 10 megawatt electric range. So that would kind of trace to potentially that leftmost swim lane in my previous slide. And we're all about inspire and educate. So we're connecting with professors and students across the globe. And so we worked with the Initiative for Interstellar Studies over in the UK. We commissioned them to develop a week-long class for us. You can actually register for it and go to our website, limitlessspace.org, and there's a place there for you to click to go register for that class. We hope to maybe get a chance to join us there. And we'll continue to try and develop those products as we move forward. So this is what I call our NASCAR chart. In our brief time of standing things up, we've been working really hard to try and reach out and formally connect with people that are similarly interested in trying to explore the frontiers of what we know to work towards these noble goals. And we've got over 17 organizations that we have formal engagements with, and we intend to grow that over the next several months as well. So we're really hard at work, and it's neat and inspiring to see that there are so many people that are very similarly wound, if you will, and they want to try and push back the darkness, if you will, and find ways to try and uncover what we don't know and try and find ways to use it to enable these bold space exploration visions that we have. So I'll just talk just a second about our internal research, and then I'll talk about the Interstellar Initiative grants winners that are doing some work for us. The stuff that we're doing internally at EagleWorks, as I said, this is kind of a frontiers of physics type of work. We're doing some work with something we call our dynamic vacuum model. This is this would be categorized as a pilot wave model, but this is again trying to find out in the process of how do you connect general relativity with quantum mechanics. Are there some deeper understandings that we can have to maybe start to fill in the gap between those 2 circles on the Venn diagram, if you will? And so this model that we're working on has some potential implications for power and propulsion for space flight. It may also provide some mechanisms for us to increase something we call negative vacuum energy density. That's kind of the secret sauce for the idea of a spacewalk or a wormhole. And then there may be some communications and sensor implications for the physics that we're trying to work on. You see there's a small picture of some custom Casimir cavity geometry that we're trying to work out the manufacturing techniques to make this stuff. This is very tiny. It's literally like we're trying to make a paramecium from scratch, if you will. So we're definitely pushing the bounds on micro and nano fabrication, but we have to go through and do analysis of these types of structures to predict how does the quantum vacuum respond to the presence of these potentials in the quantum vacuum. And so we use something that's like a string theory inspired technique called numeric world line to model how the vacuum responds to the presence of these structures. And so you see this is some of the analysis results for these 2 plates and pillar. You can see how the quantum vacuum is predicted to respond. So the reason I'm highlighting this is going to lead to my next chart. Sometimes when you're doing fundamental research, you uncover stuff that you didn't expect to find. We were just trying to study these Casimir cavities to understand how they might impact the vacuum. And so this energy density distribution that our analysis predicted for this plate pillar type of system resembles qualitatively the energy density distribution required for the idea of a spacewalk. This is a little cartoon of the Alcubierre warp metric. This is the expansion and contraction of space, and then this is a little gray cartoon of what a spacecraft might look like. And there's this ring, and this ring is filled with negative vacuum energy density or exotic matter. And so this is kind of a section cut of what that distribution looks like. And you can see there's some similarities there. But this is prismatic, whereas this is toroidal. So we took the extra step of saying, all right, well, what if we had a 1 micrometer sphere surrounded by a 4 micrometer cylinder? How does the vacuum respond to that, the presence of those potentials? And so you see, this is the little section cut here. Now this considerably close, it matches the Alcubierre energy density distribution, and it has that toroidal slash spherical distribution. So what this analysis tells us is we can potentially make a nanoscale structure, micro nanoscale structure that will manifest a real micro warp bubble, if you will. Now this is, don't get excited. This is not something, it's not going to go anywhere. It's not going to do anything, but it's going to potentially change the optics properties. And this might be something that would be interesting to see. Can we maybe explore the implications of that in the lab? So again, this crawl, walk, run type of mentality. I grew up in human space flight, and so there's lots of little steps you have to take before you go from concept to, as Holly was saying, unrolling a solar array, a new solar array on the space station based on new technological developments. So now I'm going to switch gears and talk to you guys very briefly about the 9 performers that we have for Interstellar Initiative grants. This is something that we stood up. We want to try and feed the community, primarily the academic community, to give them an opportunity to try and focus on research that traces to these types of goals of enabling bold human exploration of the outer solar system and maybe onto the stars one day. And so we have 2 categories of grants that we award through this program. One is called a tactical grant, and so that's about $100,000. So it's primarily anticipated to be theoretical, unless it's in partnership with other funders that are also funding an investigator. Maybe it could be a little empirical. And then we have the strategic grant, and that's where we would fund up to about $250K, but we do anticipate that has experimental work being done. So one of the performers we funded is Professor Phil Lubin at UC Santa Barbara. He's been doing some work on directed energy, where you have some type of a ground station and it beams power to a spacecraft, and the spacecraft could potentially use it for just power, or it may be able to use it for propulsion, maybe passing the power to some Hall thrusters, if you will. So he's going to be taking the experimental setup that he has in the lab, and so we're funding him to migrate that into the field, where he can have potentially 3 power sources that are beaming a power signal to a target, a cooperative target, and that target is collecting the power at its remote location, and so do this over much longer distances than what he's done in the lab. Now, interesting thing about this is this may be something that we could have some precursors, where maybe we would want to work with one of the CLPS, the Commercial Lunar Lander Program customers, to integrate some elements into one of those early landers, and we could have a ground station that's maybe 10 meters in diameter that would beam power to a lander that's on the surface of the moon. And although it wouldn't be able to provide power per se, it could heat the lunar surface with a diffraction pattern in such a way so that you see on the picture on the bottom right there, there's some little red dots. And so an infrared camera would see these little hot spots in the surface of the moon, and the moon would kind of have polka dots. We also funded Professor Richard Norty at Delft University of Technology. He's doing some work on relativistic solar sails, a little bit different from the solar sail you heard Max talk about. In this case, it's anticipated there's a ground station that's beaming power to the sail to accelerate it. And so some of the speeds that these things are anticipated to achieve are so fast that there's some relativistic shift on how it perceives the wavelength of the light coming from the ground station. And so they're having to come up with ways to structure the surface so that it can have high reflectivity across a large bandwidth of light, if you will, so that the sail doesn't overheat in the process of accelerating it. As I said, we have 4 teams working on fusion. Professor Ray Sedgwick at the University of Maryland, he's doing some work on a direct fusion drive where he's using kind of what we call an E cross B shear flow stabilization. Its electric field is orthogonal to the magnetic field, and that helps provide something we call shear flow stabilization. This is very desirable when you're talking about fusion, because fusion is very, very difficult. And so we're funding Ray to take his early model or his early concepts and implement some rigorous mathematical models and try to start to understand the viability of this approach. We've also funded in the fusion category, Professor Jason Casper at University of Alabama, Huntsville. He's doing some work on pulsed break-even fusion, where he's got some targets that are loaded with some fuel, and they hit it with an enormous amount of power. And so we're paying them to do some initial work to figure out the scalability. This little puddle plot you see here on the left, I don't know if you can see my mouse, but this blue area, that's where the physics coefficient of performance is less than 1. And in the yellow area, that's where the physics coefficient of performance is greater than 1. And so they're doing some experimentation to figure out where they're at with their system as it sits today and what's necessary to try and grow it so they can get those the tests where they're out here into the yellow region. We're funding Kevin Long at the Interstellar Research Center to develop a high fidelity code for inertial confinement fusion. This is a technique that's been discussed a lot in the literature for interstellar missions. You see the picture there of Project Daedalus, Project Ecoros, and a number of other teams have looked at ICF as a way to do interstellar flight. And so we're getting Kelvin to write a very high fidelity set of code that we can use to look at future concepts and get a better assessment of the anticipated performance for those types of systems. And we can look back to the literature and look at some of the older concepts to see, update the analysis based on this much more rigorous computer code that he's developing for us. We're funding Dr. Sethian Yu at Helicity Space. This is in partnership with Caltech and University of Maryland, Baltimore County. They're working on again, this is a direct fusion drive type of concept. In this approach, they have something, kind of see in the top left, there's this little donut looking construction, if you will. And this is called a plectoneme. It's kind of like this twisted rope of plasma. It's a very stable form of plasma. And so Dr. Yu is looking at having a scenario where he has, several plectonemes that combine in the entry point of a magnetic nozzle and through magnetic reconnection that heats the plasma. But then through this magnetic nozzle, this little shape you see here, there's this peristaltic type of process where the magnets are phased and they kind of squish the plasma further and heat it up significantly. And so we're paying for the model development and early hardware development for the peristaltic magnetic nozzle. This is one of our space drive teams. This is Professor John Bush at MIT. He's also working on something that fits on the frontiers of physics. It's also a pilot wave type of model, understanding of how the reality works at a microscopic level. And so we're paying him to mature his model, the hydrodynamic quantum field theory, into 3 dimensions. And in the process of studying how do you model a hydrogen atom, how do you model diffraction and some of the standard things we need to look at from quantum mechanics perspective. In the process of doing that, can we find ways to interact with this manifold? And in the process of doing that, can we impart a force to it and generate momentum, if you will? Is there a way to push off of space-time, if you will? Our second space drive team is Unlab, Mr. Charles Chase at Unlab in partnership with the Technion Israel Institute of Technology. They're going through and looking at asymmetric potentials. When you look at an asymmetric potential, potential energy, if you will, and in this case, looking at how an asymmetric potential is manifested in a resonant tunneling diode. When you integrate the vacuum fluctuations on either side of that asymmetric potential, there's a difference in the integration. So that suggests that it's possible to potentially generate a force. Again, getting back to this premise of, can we find a way to generate a force without having to carry onboard propellant? Can we have some way to interact with space-time or the quantum vacuum? And so they're doing the analytic work and working with some folks that do manufacturing to figure out what can they make, and based on the analysis, how big of a signal can this thing generate, and can we maybe measure it in the lab? And so again, this is not something that's mapping right to spaceflight, but this is the next steps we have to take to try and figure out what works, what's viable, or what's not viable. And finally, we have Professor Remo Garantini at University of Bergamo. He's doing some work on traversable wormholes. He's trying to find some ways to maybe increase the magnitude of the manifestation of negative vacuum energy density by exploring the implications of using superconductors, or maybe the topology of what you use with the different Casimir cavity shapes and so forth. And he's also going to be looking at some of the mathematics of how this works to see if there's some ways for him to further improve it. So this is my last slide. This is our university partnership. As I said, we're funding Texas A&M to do some work on a micronuclear reactor. And this is actually for terrestrial use first, right? And this is, so there's a means to an ends for this. This aligns with the DoD Pele program. And so we're trying to set up a scenario where we can say you can have a terrestrial application where maybe you impose some additional requirements to when you put out a solicitation, so that when people submit proposals to make something, they can make something to these requirements, so that maybe this whatever thing they make and they provide as part of the contract is adaptable for potential use in space. And so that's what we're trying to do with this portable nuclear reactor that fits in a ConneX container. Can we get it so that it's going to be lightweight and that we can adapt it for potential use in space? Remember back to my 3 swim lane chart, the nuclear electric propulsion. That's kind of based on known physics and known engineering. That's a very necessary avenue for us to explore. So with that, that's everything I had. So thank you, guys.
Thank you, Sonny, for this extensive presentation. And I think we're in safe hands in the future. I have a question from your colleague here, George. He's asking, will high-performance computing be required to operate these complex propulsion systems of the future?
So I can say HPC is absolutely necessary to do the analysis. The stuff that we're doing for DARPA, studying how the quantum vacuum responds to those that topology, the worldwide numeric stuff that we're doing, it requires an enormous amount of CPUs. We're currently making runs that require over 1,000 CPUs, and we want more. So we're in discussions with AWS to see if we can maybe enable up to 10,000 CPUs to go through and do some runs, because the analysis is very, very gritty. So I really kind of anticipate maybe if you ever had something in implementation, you'd probably need it there too. But we already need it now in the analysis phase that we're doing. So.
Thank you, Dr. Sonny. Nayan asked Holly, what would you say is the most difficult part of implementing and extending human presence into the solar system?
I think Sonny and Max can answer too. There's the technology piece, and they've talked quite a bit about it. But I actually think it's more, getting everyone lined up behind the same motivation. So the really good news about human spaceflight is there's a lot going on. But there's also a downside to a lot going on, because there's only so many resources, and they're spread across multiple teams, countries, perspectives, technical strategies. And so I do think that it is a little bit of a global, worldwide endeavor if we're really going to get Moon, Mars, and then beyond, sort of rally the resources and have this big audacious goal that Sonny was talking about. So to me, the people part and the motivation and getting everyone on the same page is actually maybe just as challenging as the technical piece. And I don't know if Sonny or Max have anything to add.
Max, do you want to add on? You're muted.
Yeah.
Would you like to add on? Otherwise, I'll continue with the next question for you.
Yeah, maybe you can. So you can maybe repeat the question, because you were referring to me in this sense.
Okay.
Yeah.
We're a little bit running out of time. I'll just move on with the next question.
Yeah, sure.
For you. Can you elaborate on effects of solar sail on deep space communication, as they both work on laser? So can it interfere communication systems?
Yeah, that's actually a really good question. So you have the spacecraft itself flying through space. And as I mentioned, there's the possibility that you can have a station within a orbit, for example, which beams a laser towards, or an energy source, which beams a laser towards the spacecraft to generate thrust for the light sail, for the light sail basically. And there are actually huge implications for the communication. So the first simple step to overcome this would be to turn off the laser, for example. But on the other side, when you want to beam back information, you have to and send it back. You have to either do it on a different phase or wavelength, or you have to have a really high energy source, even inside your spacecraft to communicate. But there's also the possibility that you have something attached to the spacecraft itself, which might be far away from the spacecraft. So you can communicate with this communicator basically. So you don't rely exactly, like you don't send your waves basically through the laser itself. So that are two possibilities on overcoming this issue. And I think that the preferred option would be to have something attached far away from the spacecraft. We're talking about several tens of kilometers, because the laser obviously loses its energy in radial direction when you beam it and focus it on a certain point.
Thank you, Max. This is for all. Why should we spend a wealth and accumulate funds for deep space exploration when we're currently faced with virus problems and climate emergency that could be averted with timely involvement in better research? What's the need to get humans to space when we could use the prevalent resources on Earth more wisely? Who wants to take this?
Yeah, so I can start. I mean, certainly I get asked that question a lot, because I mean there are challenges, right, here at home on the Earth. That's absolutely true, but at the same time, I personally believe that as humans, we need something to look forward to have a goal, to be inspired about. And so at just a sort of a thinking about your heart versus the technical side of it, if all we do is focus on what's going on down here, which can often be frustrating and negative, as we've seen this last year with the pandemic, last year and a half, and you don't have a goal, you don't have something to motivate you to get out of bed in the morning. So to me, human spaceflight is like it's a worldwide goal, something to get excited about. I also then think, along with that, it is important from a technology standpoint to push those boundaries. That helps us learn more about, how we operate here on the Earth. And there's multiple examples of that, but it also helps us understand, our perspective and our place in, the solar system and the world, right? And without that understanding, we're not really going to grow, as a species.
Thank you, Holly.
This is Sonny. I'll take a crack at that. That was great, Holly. It was awesome. In the process of working on the frontiers of the unknown, right? We uncover things that we don't always know exactly how they're going to impact us in our day-to-day life. But you heard me talk about when you think about physics today, quantum mechanics, right? In the process of exploring unknown in physics, right? Quantum mechanics gives us the ability to have all of our solid state stuff that we have around us, computers, cell phones, all those different things. That's exclusively due to our understanding of the microscopic world through quantum mechanics. And general relativity is, as remote as it might seem to most people. Why does astrophysics and cosmology affect me? How does that trace to this? Well, I mean, the whole premise of global positioning satellites is only possible because of the fact that GPS satellites, they make all the corrections for the atomic clocks for the speed impact on the clock rate and the location of the gravitational potential, right? So working in the unknown always generates things that have great benefits for humanity as we move forward, right? So think about space flight. We had the space program that was government stuff, as Holly was talking about. And we're seeing this transition of space from exclusively government to commercial, right? The government pioneered getting to space, and now the commercial areas starting to take that over, and you're seeing other nations get involved and new opportunities are coming up. And so you've got SpaceX that's trying to come up with this global internet type of system. I think it's called Starlink is the term, right? And so he wants to try and find ways to make that available for everybody. And so that would be something where space exploration led to that. That wouldn't be where it is today if we didn't have all those other chess pieces that led to that, right? And so I like there's a quote on the wall at Rocket Labs. It's Peter Beck's company. I believe it says, "We go to space to make life better back here on Earth." And so I would extend that thought process, right? As if we can enable humanity to try and get out to, the Mars and beyond into the outer solar system, right? Think about, I mean, the concept of scarcity is based on, well, we don't have enough of this and we don't have enough of that. The solar system is full of stuff, right? So in terms of the benefit of trying to visualize a human society throughout the solar system, that changes the definition of scarcity, right? I don't mean to get so animated over that, but I think that's really important, right? And so we don't have to be, just laser focused on here. We have to be thinking about all these other things, and we can do that. We're capable of doing that. Yes, we needed to go focus on COVID and try and bring as much resources as we could bear, but we can also do the other things as well. So, all right, I'll shut up now.
The sky is not the limit. Agree. Blaze asked, do you have any info about the Starshot mission by Euro, which wants to use huge laser systems 1 by 1 centimeter spaceship to another star and take a picture of the planet?
Who is that question for?
Anyone.
Okay. So the Breakthrough Starshot is a permutation of the concept of a solar sail. So Max gave some great charts on the solar sail. And so Starshot is a scenario where you have a much smaller sail that you zot with a ground station of lasers. It's like in the gigawatts, so it's a lot of power. But the advantage is you can have a 5 meter by 5 meter sail that can accelerate to 20% the speed of light in between the Earth and the Moon. That's it. Only takes that amount of time to accelerate that sail to that speed, if you will. And so, certainly Breakthrough, Pete Warden is on our board of advisors here. They're one of our cousin organizations. They're partnered with us on our Interstellar Initiative grants. And so some of the people that are thinking about the elements of Breakthrough Starshot, I mean, we're funding Professor Phil Lubin at UC Santa Barbara, and he was actually the guy that kind of developed some of that concept back in the day that led to Starshot. And so his beamed energy propulsion stuff that we're funding, right, to do the field test. And then we've connected him with Intuitive Machines to potentially find ways, can they do something with Nova C? Can we do an experiment where we zot some modest amount of power to a lunar lander? And then you've got Richard Norty at Delft University of Technology. He's doing that work on the relativistic solar sail. And so we'd like to consider, can we, because he can make a 5 centimeter by 5 centimeter sail with all of this this complicated structure in it. And can we find experiment, whether it's on Dragon or on the Axiom space station or Intuitive Machines, where we could do a cislunar experiment where we have a small source and we zot it with a laser and accelerate that solar sail, just as a demonstration, like Ecoros was a demonstration of a solar sail.
Thank you. Vipul asked, what role does astrodynamics play in space operations?
Yeah, so I'll start with that one. So we have, at the Johnson Space Center, a pretty strong astrodynamics team. So there's a lot of, if you talk about operations, right, and you talk about the spacewalk that we did, there's a lot of analysis that goes into the space environment that they'll be working in space. Obviously a spacesuit is like a little individual spaceship. And so we really care a lot about how they are affected because they're much more vulnerable when they're outside. So where we cross in operations, certainly in low Earth orbit with astrodynamics, is a lot about the environment that we're living and working in. So that's kind of the simple answer from our standpoint, and maybe Max or Sonny want to take it into deep space a bit.
Yeah, so astrodynamics are actually a really hard thing to simulate, because you only have it's so complicated that you cannot make the hand calculations on the paper itself. So, and the thing is, like, I'm working with, I'm researching magnetic sails, and they are based, for example, on the solar activity, so of the sun. So you have a huge range of from where, how much thrust you generate when the sun is least active and really active, or you have a solar storm coming, for example. So need to take everything into account, because what many people think is for example, in everyday life you just brake a car, like brake it and decelerate it with your foot, and that's it. But you can't do this in deep space or in space in general. So you're always depending on delta V and on the position of the planets, for example, in the solar system. So when it comes to deep space propulsion, you also have to specifically design also the solar sails and magnetic sails, depending on where you want to go. This structural issue of orientating, for example, the solar sail, that you have the right moments and the right forces acting on the solar sail, that you that the path and trajectory of the spacecraft is in the right direction. And for example, this is a big plus for the magnetic sail, for example, where you can easily orient your magnetic field much more easier than a structural fabricate. So that's one of the advantages, for example. So astrodynamics is really important when it comes to deep space travel, because you don't have, for example, in low Earth orbit, you have a kind of a stationary, I would call, conditions. And in deep space, they change rapidly. So you have the solar wind, you have the planets moving around. And when you enter the interstellar regime, you have the interstellar medium with charged particles in all kinds of directions. And yeah, so that's a big challenge. So definitely, we also, for interstellar, we need to have lots of data to run the experiments and especially the simulations. So as soon as you enter the deep space regime, it's really, really hard, actually. So you need to have a lot of smart people working on that one to make it happen.
Thank you, Max. Are propellant-less magnetodynamic drive the future of space travel? And if so, how would this work, and where are they best suitable for?
Is this for me?
Anyone.
Okay, because it said magnetodynamic drive. So I think the question relates to a magnet with a oscillating electric field, which generates a magnetic field, I assume. So so to answer that question, I think it's when you say future, I think you will have lots of different propulsion techniques, and I don't think that we can say right now which is going to be the standard in the future. Because there's so many things under development. But as I referred to, there are really lots of advantages from magnetic sails, for example. And because you don't have any propellant on board, you always have a solar wind. You can orientate it easily to correct your trajectory. And the thrust generated is actually higher than for solar sails, depending, of course, when you on the energy source. But there are also certain advancements when it comes to magnetic sails, because there are also concepts to make increase the power and efficiency of this magnetic sail by making an atmosphere around the spacecraft with plasma. So the plasma orientates depending on the magnetic field, and amplifies the effect of the blockage and drag that it exerts on the solar wind to generate thrust. So I'm really confident that it can be one of the propellant-less and deep space propulsion systems of the future, because one of them also the other advantages is that you can decelerate. So when you want to go to a planet, you also have to decelerate, right? So when you come there with a certain high speed, you have to decelerate to go to the planet, for example, and to enter the atmosphere. Because right now, every deceleration is done in the atmosphere of Mars, for example, by re-entry. And you cannot do this with extremely high speed. So you can decelerate also by just turning the magnetic sail around to have a blockage effect that generates thrust in the other direction. So you can decelerate also. So I'm really confident that it's going to be a important propellant-less deep space propulsion system in the future.
Winfrey asked, what can we look forward to in the upcoming 2030 new Voyager probe?
So, Ian, did you say the 2030 Voyager, 2030 Voyager?
Yes.
Yeah, so I am not as familiar with that one, so I'm not sure that's a good one for me to answer. Maybe Sonny knows a bit about it.
I'm with you, Holly. I am a 2030 Voyager. I'm not up to speed on that.
Okay, a brief.
I think I can answer that question. So the thing why I can answer these questions, I'm in touch with a lot of colleagues who are actually plasma physicists, and they also are really keen on researching and experimenting with plasma inside deep space. So also in the outer regimes. So the thing with Voyager is that by 2030, they have to, so the thermonuclear batteries, they still work, and it has enough power to beam back the information. So I think the main goal of Voyager in the next 10 years of the probes is to measure the interstellar medium, so the particle density, the velocity of the particles. Are we talking about more protons, like hydrogen, charged hydrogen inside the interstellar medium, or is it more electrons? Which temperature do they have? Is the trajectory, is it always constant, or do we have constant change of the stream of these particles? So I think that's the main goal of Voyager probes in the next 10 years.
Thank you, Max.
Real quick, if I could just append something. Thank you, Max. You calibrated me. I thought somebody was suggesting there was another Voyager mission. I was like, I'm not familiar with another Voyager mission. So, yeah, yes, just it's interesting. The Voyager, if you were to look at Voyager 1, right, it's closing in on, I think, 150 astronomical units away from the sun. If it were pointed in the right direction, right, it's currently not, but if it were pointed in the right direction, you were to ask how long would it take to get to Proxima Centauri. You're talking 70 some odd thousand years. So that kind of highlights how difficult interstellar travel is when you just use something like chemical propulsion and gravity assist. So.
Okay, we're approaching the end. The last two questions, a little bit more complex one here. Voyager 1 didn't find any leakage of particles from our sun, but Voyager 2 recorded a small trickle of solar particles streaming through the heliopause, which is the total opposite of the Voyager 1 result. After comparing the contrasting data, what are the results of the study? Max, that's for you.
Yes, so as far as I understood the question, so there's a differentiation between the measurements did by Voyager 1 and Voyager 2, right? And can you repeat the last part, please?
After comparing the contrasting data, what are the results of the study?
So I'm not familiar with the study itself. What do you mean my study? So I can give a background on what I know currently on the deep space and heliosphere. So what we know is that the amount of interstellar particles, we are mostly talking about protons and electrons, they move in a certain direction through the heliopause, and they have a temperature of 2 million kelvins on average. So it's a really a high temperature, high energy source coming even when you are in this high vacuum regime inside where you only have 1 million particles or even less particles per cubic meter, which is really low. And I'm familiar with this because you also have to take into account when you have interplanetary and interstellar travel with magnetic sails, you always have to have a charged particle stream. And so it's really interesting that what I was referring to earlier, that you need to decelerate also the spacecraft. So the results from Voyager 2 and 1 are really important, and I think that they're headed also into a different trajectory, right? And it might be possible that the interstellar medium has different properties in different regions in the solar system. So this might be also a important aspect when you want to go somewhere, that you need to know, for example, with magnetic sails or solar sails, that you need to know the interstellar medium properties at these certain positions. So I think it might be important to also know the properties of interstellar medium at different locations. So in the future to send some probes there. But I don't think we have a definite answer on how it is exactly. We only have the data of these two missions. So that's going to be quite important when we look at interplanetary and interstellar travel in particular.
Thank you. Two last questions. You have 20 seconds to answer that before we do the closing. What is the principle behind the origami photonic crystal sail fabrication? 20 seconds.
20 seconds. The origami, so they're trying to go through and create a structure that interacts with multiple wavelengths of light at the same level of reflectivity, right? So it's kind of capitalizing on manipulating micro nanostructures so that interacts with the incoming wavelength in such a way so that whether it's red or a little less red, it can reflect at 99% reflectivity. 20 seconds, less than 20 seconds.
Thank you. Anyone wants to add on? Okay. How is quantum field theory applicable for vacuum-based propulsion?
Well, that's I think that's the thing we're trying to figure out, right? In the process of trying to explore between quantum mechanics and general relativity, or is there a deeper understanding that we can have beyond this standard model of quantum mechanics, where we can understand the characteristics of what the background field or fields are, and in the process of mapping that out in the mathematics, can we find ways to maybe interact with it in such a way so that we could generate a force? And so that's the thing that a couple of teams are trying to do, including us. So remains to be determined.
Thank you. With that, we'll thank everyone for your attentive questions, and thank you for your participation. Thank you for our esteemed guests, for your devotion, dedication for human space exploration. Any further questions, please, we may follow up again. So thank you, everyone, for your participation, and we hope to see you soon at the next episode, which is July 10th, the Humanity's Sustainable Presence on the Moon. How can partnerships help shaping a sustainable lunar economy?